So you have these authorities that then.
In this YouTube video that I made with Philip Trudeau, or on this video, I received a comment which we will today be addressing and explaining with some basic questions. Well, they're not basic, but whatever. Anyway, so let's go. I know the basics of how DNS works, but what I always wonder is whether or not they implemented anything for the man-in-the-middle attack. Let's say you want to query for an IP from the root servers, but there is a man in the middle who returns you a different one. Does DNS do anything to prevent that case? Or because the wrong server certification already doesn't match, so it just doesn't matter? The answer is, let's imagine we have our computer here. How do you draw a computer these days? Like a little TV. So you're on a network, right? So you connect to your local network box thing. I don't know, which kind of looks like an old TV. The way DNS was designed is that back in the day, you just trusted your network. So basically, the idea is that, I'm on a computer, I'm connected to an institution, like Harvard or something, or maybe a cool university like Berkeley. So I'm connected to the Berkeley institution, and so they are providing me with a service of being able to look up DNS names. And I trust my institution, and so I have this. I'm receiving the names from them. It is an assumption in DNS. Also, this is when the internet is young, right? So most of the traffic was unencrypted anyway. And so DNS is just this way where, sort of in the network hierarchy, okay, you'll connect to a network. The network will tell you about a DNS, or will have a DNS server, and then it has somebody it trusts further up, and further up, and eventually gets the ICANN. Yeah, the idea in the question is absolutely correct, that somebody can just do a man-in-the-middle attack, report a different domain server. And in fact, this is one of the reasons you have to do the certificate stuff. It is true, though, that because of the certification process that was added with SSL and TLS, the fact that you can do this kind of man-in-the-middle attack doesn't matter. It matters in the sense that this person here will try to connect to a web address, connect to youtube.com, and their browser will, do a big warning sign that says, "Whoa, this youtube.com we're connecting to has a bad certificate. You go back to safety." Right? And for that reason, it will not work. It's still a bad experience, though. But the point is that nobody ends up doing these. They're very uncommon because of the fact that your browser will detect this. Anyway, so with that out of the way, what is the next question? Expanding on the last question, there's just two ways, or there's just no way for you to store all the certificates on your computer, right? I don't know specifically what a certificate stores, please tell, but at least it must have a public key and the website's name and IP. And we could actually look at this right now. So, connection is secure, certificate is valid. Here we go, this is what the certificate contains. So there's just various data, some dates, some fingerprints. Google Trust Services, I guess this one comes from. And yeah, we can see which algorithm is being used. There's a bunch of stuff in here. We'll look at that. There's some DNS names. Anyway, I mean, you could go inspect the certificate that you're using in the web browser to connect to something. But the reason why... Oh yeah, so the way this works is that when we connect, when we initialize a connection, so say our client is over here. Sorry for my bad writing. When we send the connection, this will be simplified, but it'll get the point across. We send the client hello, like so, and then the server. This is in an HTTPS connection. When we send the client hello, the server will respond with the server hello, which includes a certificate. So it will send the server hello, and it will contain the certificate. Now, the certificate by itself isn't very interesting. It doesn't tell us that much. Except this certificate is signed by a certificate authority, or a CA. Perhaps, in fact, this one we were looking at here. Yeah, that's funny. Yeah, so you can see here the sort of trust, I guess, trust hierarchy here. And we get up to default trust. It's not very intelligible to me, but in this situation it might be Google Trust itself. But so look, you have a certificate authority. The certificate authority has signed this certificate. So as long as you on your client side have a list of certificate authorities that you trust, then you trust these and you store them on your computer. So the certificate you receive, you go look up in this list. Hey, is it signed by this guy? Is it signed by this guy? And it will be signed by one of the certificate authorities, which is installed by your browser, often. Or, well, by Microsoft or whoever your OS vendor is. In the case of Chrome, I think they install their own stuff as well. And that is why, to answer the question here, storing, yeah, so we don't store the thing for every single website. We receive, after having connected initially, we receive a certificate that is signed. And then it is signed by somebody who is installed on our system. Now, the final question, why do you need to do a Diffie-Hellman exchange? I know that shared secret is faster than asymmetric encryption and doesn't have key leakage problem, but why specifically shared though? Can't the server just decide on secret key and send it to the client or vice versa? There are two answers to this question. One is yes, you can just do this. And the other is that also, yes, this is now done. Now that Diffie-Hellman can no longer be used. But let's go through that. So, basically, standard RSA, you have a public and a private key pair. You have these keys. How do you draw a key? Is it? Yeah, like that. Okay, so the thing to realize about these is you have to be worried about something called key leakage. So if I have some data, which I'm going to represent as this wavy line, that goes through this key, and then it becomes some shuffled piece of data. Again, we're simplifying a bit here. Let's say it becomes this very wild thing. And then we go through this one again and we come back to our original. Basically, okay, imagine you were looking at these two pairs, okay? If the encryption scheme is done well, it's very hard to figure out by looking at what I put in and what I got out to figure out what the key is. In this case, normally you wouldn't encrypt. Well, no, you wouldn't encrypt with the public key. You're trying to figure out the private key because it's asymmetric. So anyway, the point is, the more data that flows through these, the bigger the surface area for mathematical attacks is. Because it turns out, no, actually you can, if you capture lots and lots of data over time, small bits of the key leak out. So at least for old style cryptography, basically the idea was, hey, if we use our public and private key all the time, it's going to get leaked. And so we can't use it on every web request. It also is a little bit dangerous in the sense that that means when we're connecting to a server, every server would have to have an official Google private key on board. Which wouldn't be that bad, or wouldn't be that good, because then it could be leaked, etc. So the reason you want to do Diffie-Hellman is because we can send the certificate, and then we do this, Diffie-Hellman key exchange, and we can establish a secure connection without having used our private and public keys, and that's good for keeping, for not leaking information. The question though about can't the server just decide on secret key and send it to the client or vice versa? And the answer is yes. And since Diffie-Hellman now is broken, that is what is done. So in modern quantum crypto schemes like Kyber, for example, if we have, say, Kyber 512, which is the sort of low-end thing, the way Kyber 512 works is exactly this, where the server or client, I mean, it tends to be the server in sort of more traditional installations. The server will pick random role, shared secret. We say shared secret because it's shared between the two and nobody else knows about it. So it creates a shared secret, an SS. And then it uses a ginormous... No, it's actually the opposite. So the client generates... What happens is that the client receives the server's ginormous secret key, I think, or public key, and then it uses, this is like a huge thing because it's cool, like quantum stuff, quantum resistant stuff. The client, I think, will generate a shared secret and then encrypt it with this huge key into an even more ginormous payload. With tons and tons and tons and tons of data. Like this, it's an inflation. This thing is about 16 or 32 bytes. This thing on the other end will be about 1,000 bytes. It's a huge inflation. Then this gets sent to the server. Where it is decrypted. This huge ciphertext is decrypted back into the shared secret. So the answer to your question is, why do we need a Diffie-Hellman exchange? We don't. It was good because it meant that you could RSA keys in particular, to my understanding, and also elliptic curve is a lot more. Yeah, especially RSA. Elliptic curve is maybe more fine. But these traditional schemes, asymmetric schemes, were very susceptible to key leakage. I guess, yeah, you mentioned the key leakage problem here. So you're aware of that. But yeah, so I mean, the answer to your question is yes, it was because of key leakage problem that you didn't use that before, but now we can't use Diffie-Hellman, and so this technique you describe of just sending an encrypted key is what is used. You'll see this in CryptoSphere. This is called a KEM or KEM. Key exchange mechanism, which would have been Diffie-Hellman before, but now is just a really, really robust way, or really, really robust form of asymmetric encryption to send, and they specifically build these schemes for sending 32-byte payloads, because that's the size of your symmetric key. Normally you have 16 bytes. The craziest schemes, 256-bit encryption uses 32 bytes. And what's cool about this is if you have a key exchange mechanism, you can just convert that into a general purpose asymmetric scheme for bigger pieces of data. Because if I can send you so imagine I send this huge ciphertext. So okay, in my payload to you, I send my public key. So you can decrypt this thing. Then I send a ciphertext, which is also huge. Okay. And then I send data encrypted via the secret key that is in this ciphertext. Okay, so you receive this public key. You can match this against the list of public keys you have yourself to know that you trust that or whatever. And then you use these two to decrypt into a. No, what am I talking about? This is stupid. No. Okay, the reason you send a public key is because you have to say which key I used. That's right. So you send to the server, you say, hey, I used this public key to encrypt this ciphertext. You have a corresponding private key. I guess they call them secret key. SK. You have in a table somewhere, you have a PK-SK table in the server. And so I send this thing to you. I say, hey, I use this public key. You match it. You then use this secret key combined with the ciphertext to produce out the shared secret. Then you use this shared secret to decrypt this data. Okay? And what this means is by using a post-quantum key exchange mechanism, we've turned this small size only key exchange mechanism that is very good at not leaking. Because we can send the 32-byte payload, we can send a secret key, which means that then we can send an unlimited amount of data afterwards that is encrypted with said secret key, which means, in fact, our key exchange mechanism can be turned into a general purpose asymmetric encryption scheme by combining some symmetric encryption as well. And I believe I talked about that in the other video that we did of these live streams. So the comment was on this live stream. I talk about this in this
That's
video.
because I know
Somewhere in here. Yeah, look at this. Oh, but we have a variable in this, and then it's like a.
Okay. So we're taking the TCP principle of like we're not gonna unconditionally include acknowledgement in our packets.
Yeah. Anyway, we talk about it here.
Well, I was disappointed at this fact.
And many other things in this redesigning the internet from scratch stream that we did immediately after the previous one, and only 820 people have watched this. So there's a lot of gold in this, including designs for future alternative DNS schemes that are planned for Serena. Anyway, thank you for your comment, Mr. Than Long Tran. And you should go watch the other video. Have a good day, everybody.